Hello, my name is Robin Mitchell, and today Electropages is here at Embedded World in Nuremberg, and I'm joined by...
My name is Peter Canty. I'm the Systems Applications Manager for the Industrial Connectivity and Control Group with Analog Devices.
Fantastic, it's great to meet you.
Same here.
So could you just give us a quick rundown of what's going on in this demonstration here?
Sure. So what we're looking at here is a new Ethernet technology for industrial applications called 10BASE-T1L Ethernet. So the T1 refers to a single twisted pair, so there's only two wires in the cable.
Twist.
Exactly. And L then refers to long haul. So the specification actually supports up to 1 kilometer of cable length and providing 10 megabits per second over that cable length.
And this is what we were just talking about before we started recording. And I couldn't believe that you can get 10 megabits down a 1 kilometer cable.
That's correct.
Absolutely insane.
Yes, and the challenge then is the analog challenge of receiving that signal, which is now attenuated across that cable, and then doing the signal processing to recover the data out of it.
And the other thing as well was that the voltage shift was quite small as well, wasn't it? What was it again?
So it's 2.4 volts in the high voltage case, and then in safety applications like APL, it's actually only 1 volt.
And so there's not really much, like wiggle room in terms of what the signal can do.
And that's why it's a difficult analog challenge, which is what we do particularly well.
Now, why is it that an industrial environment would want to use a single twisted pair cable? What advantage does it bring to the engineer?
So if your typical Ethernet cable has 4 twisted pairs, your Cat5 or Cat6 cable, the fact that there's only a single twisted pair obviously has a big impact in terms of the cost of the cable.
Yeah.
It also allows you to retrofit using previously installed cable for other standards like RS-45 or CAN, and actually be able to fit modules at either end.
That's quite interesting. So you could have a pre-existing installation, you take out the sensors and the hardware, but you still got the cables left behind, so you can replace it without having to redo cable management.
Which is a massive cost if you have to go down that route.
It can be absolutely, it can be absolutely nightmare. So could you also just explain what's going on with this board here as well?
Right, so this is also 10BASE-T1L, but the focus here now is SPOE, or power over single pair of Ethernet.
Seriously?
Yeah.
So not only have you got a single twisted pair cable, but now you're trying to push power down it as well.
Yes. Well, we've actually managed to do it, so it is working. Yeah.
That's insane, because power over Ethernet's only really just come out like in kind of like wide usage. So I mean, it's been around for a while, but not. Like, it's not something you find on everyday devices still.
That's right, but the fact that has gained traction has made it attractive as a concept for the single pair
Even
case.
for single twisted pairs.
Yes. Yeah. So to be able to power a node like this down that 1 kilometer cable and have the data on the same pair of wires is obviously a very attractive thing from a cost perspective.
And so when this thing transmits power down the cable, is it using AC or DC?
It's DC power.
Oh, it's DC?
Yeah.
Oh, right, okay, that's quite interesting. So, with the exception of the fact that this is using power down a very long cable, which in itself is just completely mind-blowing, what else is going on with this example?
So, these devices, kind of in your standard PoE case, are actually communicating with each other. So, when you want to bring a link up, these will actually talk to each other over SCCP. So the node here will say, I need X amount of power. The power source equipment on this side will determine whether it has enough power to supply this request. And if the answer is yes, then the power is applied, but not before that. So there's intelligence in making sure that a device that's not suitable for the bus is not connected to the bus.
Oh, so it will take the power it needs to realize that it can't use the power.
It will define its characteristics and say it wants a particular level of power, and then the PSE device.
And so it sends that message back, and if it can't do it, it'll say, no, we can't do that.
Yes, and it literally will not.
Like a negotiation.
Exactly.
Oh, brilliant. So brilliant. So I think you've got it up to, you've connected something to a camera here, haven't you?
Yes.
So could you just talk about how you're using the single twisted pair system to stream video content?
Okay, so basically what we're doing is a media conversion exercise here where we have data coming from the camera into a standard Ethernet connection here. We then put the 10BASE-T1L Ethernet back to back with that to do the media conversion. That is then allowing the signal to pass through this cable. and then you have a 10 base T1L on this side, and you do the reverse exercise here to give you back the data.
And it's this card here.
That's correct.
That's the not the bridge, but like the what would you call it?
This is the power module and media conversion.
Oh yes, media conversion. Sorry. Oh right, of course. So I'm taking this large transform here is probably what's dealing with the power conversion.
Yeah. So it's not the module that's necessarily needed for the amount of power being used in this instance. This is probably a higher power one. But you get the idea.
And I'm not sure if I asked the question, but what kind of voltages are we pushing down these cables when we're doing power as well?
Okay, so that can be, there's two classes of power, so it can be either 24 volts or 50 volts.
Oh, it's quite high then.
Yes.
I suppose you have to if you're going over big distances.
Exactly.
So you have to account for the loss.
Right.
And then you're superimposing that your signal on top of that power.
That's correct. Yes.
Yeah.
So you basically AC couple the data.
That's right.
And you DC couple the power.
So you've got your 50 volt signal, which is your DC, and that's your power. But then you're superimposing your AC signal on top of that. So you're sort of wiggling on top. So you've got both your power and your data.
There you go.
That's absolutely fantastic. So I think we should now move across to the second demonstration that you've got here, which is, I think, IO-Link, is it?
So this is IO-Link. So if the technology over here is focused on process control,
this one over here,
the 10 base T1L, this is much more about factory automation. So this is more suitable for an environment where you have a highly modular factory floor and you've got lots of sensors proliferated around it and actuators that you want to control, motors, etc. So ADI has one of the most comprehensive portfolios for IO-Link in the industry, and that's both on the master side and on the device side, so both sides of that IO-Link. So here we have an IO-Link master, which can support up to 8 different nodes.
Okay.
And we've got one here connected. And what we're doing here, or demonstrating here, is the fact that we are offloading from the processor here using the PHY here. It has a data link layer included, which means it's managing the communication between these two, as distinct from the processor here doing that management. Which means that processor then has more bandwidth to do the algorithm to position this ball on this bar. So it's basically anything that would be time sensitive or interrupting is not getting to the processor such that it has to interrupt the algorithm work here.
Right. I think I've seen these before. So in industrial control systems, especially where like balancing a ball on a cantilever, is it a cantilever?
No, cantilever is more like that.
Yeah, it's pivot, isn't it?
Yes.
Yeah. So balancing a ball on a pivot is quite an intensive task in terms of you've got to respond to it very fast.
Yes, exactly.
And traditional Ethernet has an issue with, and there's a word for it. It doesn't do real-time messaging, but it's a...
time-sensitive networking?
Yeah, that's it. TSN, yeah. And so... Because
we're not talking that here.
We're not talking about time sensitive.
So Ethernet is not involved here at all. This is a different IO-Link, or different comms standard called IO-Link. Okay.
And so what data is being transmitted from this controller to this link here?
So basically, this is pinging this device every so often to make sure it's still connected, still the correct device, etc.
Right.
And it does that periodically, but it demands a response pretty quickly, which if the processor here had to respond to that, it would start
upset.
Exactly.
Right.
So it's offloaded, and therefore this can do its job.
Okay. So I see. So what you've got is a communication system, so you can get data in and out from the controller on here. But when it needs to make routine calls, say, are you alive and are you the right device? Your onboard PHY will actually handle that communication and say, yes, everything's fine, but please don't disturb the main controller.
Yeah.
Oh, right. Okay, that's interesting. And so engineers would prefer to use something like this even over single twisted pair Ethernet, even in time-sensitive network applications, when something is very, very crucial.
That's right. Crucial, and have lots of them, and also have very small form factors because they need to go in small locations. And when they're that small, they tend to generate heat as well. So a lot of the focus on our portfolio is based on reducing the heat, reducing the size, robustness, because they tend to be in a pretty harsh environment.
How interesting. And could you just give us a quick rundown of what's going on the screen here?
Sure, yeah. So basically, this is an application that's allowing you to control the arm here. And we talked about the comms here. So basically, when you start up this software, you query it, and the iLink master will actually go out the controller will actually go out and look for the IO-Link devices on the bus, if you like, and identify those. So it's identified then this particular device here.
It's got a picture of it as well here.
That's right, which is typical of how these get described in their IODD files or device description.
Just a quick question. This is a generic piece of software? Or is this specifically written for this example?
This is specifically written for these types of devices, yeah.
So some poor engineer out there has had to decode all of this for this simple example?
So a third party actually develops the tool, and that's the tool that we actually...
I was about to say, because that looked quite extensive for a single application.
We basically provide this tool as, the evaluation enabler. The stack underneath this then is something that a customer can actually implement.
That's absolutely fantastic. So if there are engineers out there who are watching this video, want to explore the IO-Link as well as the single pair Ethernet, what would you recommend that they do?
Go to our website. If you look up both IO-Link or 10-base T1L, or indeed our ADI Cronus brand.
Oh, yes.
Sorry.
Yep.
You'll find comprehensive information on both these technologies right there.
Fantastic.
Okay, thank you.
Thank you.